Dear students, after studying this module, you shall be able to know what is an allylic system with orbital pie chart, learn mechanism of nucleophilic substitution at carbon center and at aliphatic trigonal center, learn about nucleophilic substitution at the vinyl carbon, study the SNI reaction and evaluate factors affecting the SNI reaction, and analyze rearrangements caused by the SNI reaction. Introduction. Generally, nucleophilic substitution reactions are involved in direct displacement at a carbon center. The carbon that is bonded directly to the leaving group is the target for the attacking nucleophile. This process is known as SN2 substitution and is greatly studied in detail, students, in the previous modules. Generally, primary alkyl halides undergo substitution by the SN2 mechanism and do not undergo SN1 reaction. However, a primary allyl halide is very reactive in an SN1 reaction. For example, an allyl halide is more than 30 times reactive than the simple ethyl halide. Allylic substrates are usually accompanied by rearrangement known as allylic rearrangement. In an SN1 mechanism, the carbocation intermediate would have two possible resonance forms. This is likely in cases when the allyl compound is unhindered and a strong nucleophile is used and the products will be similar to those seen in the SN1 substitution. Thus, reaction of 1-halo 2-butene system with nucleophile, that is a strong nucleophile like NaOH sodium hydroxide, gives a mixture of 2-butene 1-ol and 1-butene 3-ol. So you can see how it is resonance stabilized and how with a strong nucleophile in the allylic system the nucleophilic substitution is taking place. Students, generally the incoming nucleophile therefore is going to attack either the C2 carbon originally bonded to the leaving group or alternatively at C4 carbon. These two events would lead to different substitution products B and A respectively. Now you can see here how attack of the nucleophile at C2 and C4 is going to give you two different products, that is A and B. The mechanisms leading to product A are referred to as nucleophilic allylic substitution. They are also sometimes referred to as 1,4 substitutions according to the numbering system from where the leaving group is designated to the atom. If the conjugated pi orbital system extends further, more allylic substitution products can also result. Like consider the example where 1,6 as well as 1,4 and 1,2 substitutions are possible because the system is having multiple allylic systems and so on and so forth. You can imagine how apart from 1,2, 1,4 and 1,6 systems are also formed. Just see the numbering in this compound. This is a simple allyl halide with two double bonds. For example, just consider the hydrolysis of 1-chloro-2-butene. You can see here that there are two kinds of products formed, again because there is only one double bond present in the system. So there are two possibilities, that is 1,2 and 1,4 again. Now students, two distinct mechanisms for aliphatic nucleophilic substitution are SN1 and SN2. In terms of the stereochemistry, the SN2 process is attended with inversion of configuration where substitution occurs at a chiral carbon. The SN1 mechanism involves inversion and retention of configuration, that is giving you racemic mixture. The question that arises is whether there are cases in which there is retention of configuration in SN1 reactions. The answer is yes. Besides the NGP in SN reactions, there is another important mechanism labeled as SNI which will clear all these questions just asked. Now, before going to this SNI mechanism, we would like to briefly discuss the allylic system according to the orbital pie chart. The positions adjacent to C double bond C often show enhanced reactivity compared to simple alkanes because of the proximity of the adjacent P system, that is P-pi double bond systems. Such positions are referred to as allylic. Now I would like to recall here students that the term vinylic is used to describe the atoms which are directly associated with the C double bond C unit. And you can see here the allylic carbocations formed in the figure. Thus, in allylic systems, C1 and C3 each carry a partial positive charge and both are attacked by nucleophile, which leads to formation of two products as mentioned earlier. Now you can see here what we are trying to say from this particular figure, how the two products are formed. The resonance stabilization of the allylic carbocation is presented as above in the orbital picture, as already told you. The positive charge is delocalized over two carbon atoms by overlap of the filled p orbital of the pi bond with the vacant p orbital of the carbocation. Nucleophilic substitution at an allylic carbon can also take place by an SN2 mechanism in which no allylic rearrangement usually takes place. However, allylic rearrangements can also take place under SN2 conditions through the mechanism in which the nucleophile attacks the gamma carbon rather than the usual position. This mechanism is known as SN2- mechanism. The SN2- rearrangement normally occurs exclusively when the SN2 process is sterically hindered. Now you can see this how the SN2- mechanism is taking place in this figure. Thus, the p orbital system of the double bond can stabilize an adjacent carbocation by donating electron density through resonance. Due to the stability of these allylic cations, they are readily formed as intermediates during chemical reactions. For example, SN1 reactions of allylic halides, that is allyl chlorides, bromides and iodides are good substrates for substitution reactions. A variety of nucleophiles can be used to generate a range of new functional groups from these reactions. The process can be complicated by the allylic rearrangement, where the nucleophile can attack either of the deficient sites, giving rise to more than one products. Now we come to next topic, which is the nucleophilic substitution at the carbon center. Now here we would like to give you a comparison of the primary carbon center and the secondary carbon center, and what is the difference in the nucleophilic substitution amongst these two processes at the two carbons. Now I will take up the differences side by side of primary and secondary. Let us begin with the first difference of the nucleophilic substitution at primary carbon center. The pi framework of p orbital provides stabilization in the transition state. This improves the rate of the SN2 reaction and also causes the SN2 reaction to be favored over SN1. Now on the other hand, for the secondary carbon center and the nucleophilic substitution, this subclass of nucleophilic substitution occurs when the nucleophile, that is HS-, let us say, attacks the alkene instead of the saturated carbon, that is the SN2- mechanism takes place. This is due to the saturated carbon being hindered, thus it is a secondary carbon, making the regular SN2 mechanism less favorable. So you can see how in primary SN2 is favored and the secondary SN2- is favorable. Now students, this is clearly shown in the figures of the primary carbon center and the secondary carbon center, the nucleophilic substitution and the main points of difference. Let us talk about the second point of difference for the secondary carbon, that is a pi framework of p orbitals provides stabilization in the transition state for the secondary carbon atom and the nucleophilic substitution henceforth. This improves the rate of SN2 reaction and also causes the SN2 reaction to be favored over SN1. Another key aspect of this reaction is the change of configuration at the carbon from S to R configuration. This is because the backside of nucleophile attacks the leaving group. Thus, this leads to change of configuration. Okay students, moving on to the next topic, which is the nucleophilic substitution at an aliphatic trigonal carbon. Nucleophilic substitution is also important at trigonal carbons, especially when the carbon is double bonded to an oxygen atom, sulfur atom or a nitrogen atom. The nucleophilic substitution occurs through tetrahedral mechanism, often called as addition-elimination. Although this mechanism displays second order kinetics, it is not the same as SN2 mechanism. Now students, you can see this in the figure here. In tetrahedral mechanism, first the nucleophile Y attacks to give a tetrahedral intermediate containing both X, that is the leaving group, and Y, and then the leaving group X departs. The tetrahedral mechanism is supported by the second order kinetics and also isotopic labeling techniques. In some cases, tetrahedral intermediates have been isolated or detected spectrally. When the reaction is carried out in acid solutions, the hydrogen ion acts as a catalyst. The rate of the reaction is increased as it is easier for the nucleophile to attack the carbon when the electron density of it has actually decreased. Now you can see this in the figure. Now let us look at the first step, where you can see the attack of the incoming nucleophile, then the departure of the leaving group in the second step, and finally the regain of the double bond with the heteroatom in the step third. Now this was the nucleophilic substitution at the trigonal carbon. Now we shall discuss about the SNI reactions. The label SNI stands for substitution nucleophilic internal. The reaction between alcohols and thionyl chloride has been studied extensively under this label. A thoroughly studied example is alpha phenyl ethanol. Now you can see here the basic reaction of alpha phenyl ethanol with thionyl chloride and how it gives you the similar product at the end after the substitution, forming the SNI mechanism. It was found that the product chloride is formed with complete retention of configuration on the starting alcohol. The reaction proceeds with the formation of a chlorosulfite ester which collapses with elimination on SO2. The esters can be isolated. The reaction is common with aryl methanol, that is ArCHOHCH3 with the general formula, but not with other alcohols. The chlorosulfite ester could form the product by SN2 with inversion, SN1 with racemization. In the present case, however, there occurs total retention of configuration identity and a new pathway is likely to operate in this case. Now let us talk about the mechanism of SNI reaction. On the basis of experimental facts, the mechanism of SNI is step 1. The first step is the formation of chlorosulfite ester, which is an intermediate. Step 2 is the dissociation of chlorosulfite ester to form an ion pair, not dissociated ions but an ion pair. Step 3 is because the geometry of the ion pair, the chlorine atom is forced to attach to the carbonium ion from the same side as original CO bond of alcohol. That is, it forms an internal attack. As you can see here in the figure, there is no external attack but the internal attack from the same side. Another example of SNI is the reaction of 2-octanol with phosgene that proceeds with the retention of configuration again, and as you can see here, the 2-octanol is reacting with phosgene to give you the substituted product but with the retention of configuration because of the internal attack again the SNI mechanism. It is interesting to note that if S1-phenyl ethanol and SO2Cl react in the presence of tertiary amine such as pyridine, the product R with the configuration 1-phenyl ethyl chloride is obtained. That is, inversion of configuration generally occurs. The pyridine reacts with HCl, hydrochloric acid, and produced in the first step to form pyridinium hydrochloride, and the chloride ion, being an effective nucleophile, attacks the alkyl chlorosulfide from the back via a normal SN2 reaction. Thus, we can say that in presence of pyridine, reaction follows a SN2 reaction mechanism, while without pyridine, the same reaction follows the SNI mechanism. See, another example we are going to take here for the SNI is that of plus, that is a sign of rotation, malic acid. Now you can see here, in the presence of pyridine, it follows the normal SN2 path as expected. However, in the absence of pyridine, in the presence of thionyl chloride, it is going to follow the SNI mechanism, and the product is going to be with the retention of configuration because of the internal attack which is there. Now let us study the rate of SNI reaction. In SNI reaction, both the reactants are the crucial components and they both play crucial roles in completion of that reaction. Thus, the rate will be directly proportional to the reactant and catalyst therefore. Then we can say that the reaction follows a second order rate equation. For example, rate equation in case of chlorination using thionyl chloride, as we have already taken previously, comes to the rate is equal to K, concentration of the alcohol and concentration of thionyl chloride. Note here students that the rate of decomposition of the intermediate chlorosulfite ester increases with increase in the polarity of solvent. Next comes the rearrangement by the SNI mechanism. The substituted allyl alcohols generally react with thionyl chloride in the medium of ether and form substituted allyl halides, that is, or allyl chlorides. Now you can see here in the presence of ether and thionyl chloride, these allyl alcohols, they form substituted chlorides and at different positions as discussed earlier. It is interesting to note here that the primary isomer principally gives the secondary chloride, while the secondary isomer principally gives the primary chloride. Ordinary allylic rearrangements in SN1 or SN2 could not be expected to give a 100% yield isomer in both the cases, and the mechanism may be explained by the SNI type of reaction in which 6-membered chlorosulfinic ester is supposed to be formed as an intermediate. The halogen atom binds itself to the gamma carbon of the allyl alcohol, accompanied by simultaneously shifting of the double bond and elimination of a molecule of sulfur dioxide. Now you can see here the formation of a 6-membered chlorosulfinic acid intermediate, which gives rise to the product which is formed and explains the reason for it also. This is only happening because of the SNI mechanism. We cannot explain this reaction on the basis of SN1 or SN2 mechanism. This type of reaction is called internal substitution with allylic rearrangement, abbreviated as SNI, and thus appears to be favored reaction path with allyl chlorosulfides in general. Now, having finished with the SNI, the allylic carbon, etc., we will take up now the nucleophilic substitution at the vinyl carbon. The subject matter under the title is concerned with nucleophilic substitution at unsaturated carbon centers such as the vinyl chloride. Students, I hope you remembered I earlier in this module told you that vinyl carbon is the one that is the substituted, or the X, or that is the halogen or any other substituent, is on the double bonded carbons, either one of them. Now under normal conditions, nucleophilic substitution at vinylic carbon is extremely slow compared to substitution at saturated carbon. Now if you remember, I had told you that the carbons which are adjacent to the C double bond C system, they are reactive. However, the doubly bonded carbons themselves are very unreactive and they are slow in reaction. Vinyl substrates are essentially inert towards nucleophiles. There are two reasons for this lack of reactivity. In fact, most of contexts, vinyl halides and related compounds can be considered essentially inert towards most nucleophiles. There are two reasons for this. First, a vinyl CX bond, as I already told you, is stronger than the alkyl CX bond because of the resonance interaction between the double bond and the lone pairs on the halogens, that is the unshared pairs of electrons on the halogens. This interaction also weakens and polarizes the pi bond which is there, which is why such compounds are reactive towards electrophilic addition rather than nucleophilic substitution. The second reason for low reactivity of vinyl substrates towards nucleophilic substitution in particular is that SN2 transition state as well as SN1 transition state or intermediate, that is a vinyl cation, are too high in energy to be readily accessible. So, let us take an example of this. The heterolytic bond dissociation energy of vinyl chloride is 207 kilocalories as compared with 191 kilocalories for ethyl chloride and 227 kilocalories for methyl chloride. Values for fluorides, bromides and iodides show similar differences. It takes around 16 to 18 kilocalories more to break the CX bond in a vinyl halide than in the corresponding alkyl halide, that is the let's say ethyl chloride. Except for the bond in methyl halides, this is the strongest CX bond we have so far encountered. The bond length for vinylic CCl is 1.73 angstrom compared with 1.78 angstrom for the saturated CCl bond. A shorter bond in general and a stronger bond thus are difficult to break. Thus, the rate determining step involves the breaking of the CX bond, as it will be very slow to break such a strong bond. The bond in vinyl halides is harder to break and thus the reaction is slow. Now, this explains its non-reactivity towards the nucleophilic substitution reactions. Not surprisingly, the difficulty of generating vinylic cations by heterolysis has been taken as a challenge by organic chemists, and the work done mostly since about 1970s, vinylic cations have emerged as accessible intermediates with fascinating properties. Many people from many countries have been involved in this research of isolation of vinylic cations. The vinylic cations can readily be made through solvolysis of the SN1 kind when the two conditions are met. First one is that the leaving group should be an extremely good one, and the second is the vinylic group should contain electron releasing substituents. Most commonly used for this purpose is the super leaving group, that is trifluoromethyl sulfonate, which is known as the triflate. Now, this is a very good leaving group, and if this is a good leaving group, then this vinyl cation can be easily accessible for study. The powerful electron withdrawing F atom through dispersal of the negative charge helps to stabilize the triflate anion and making the parent acid, that is CF3SO3H, the triflic acid, one of the strongest Lowry-Bronsted acids known, much stronger than we generally come across, that is sulfuric acid and HClO4. The triflate anion is correspondingly an extremely weak base and one of the best leaving group known in organic chemistry, and it is used in lots of purposes in organic synthesis. Taking an example, students, towards solvolysis, saturated alkyl triflates have been found to be 10,000 to 10 lakh times as reactive as the corresponding tosylates and as much as 1 billion times as reactive as the chlorides or the bromides. The electron releasing substituents in the vinylic moiety are commonly aryl groups, but alkyl groups are sufficient to allow the reaction by SN1 mechanism. Now, let us take this example as shown. Substitution at vinylic carbon by another mechanism. Substitution at vinylic carbon is greatly facilitated in vinylic compounds of the type ZCH double bond CHX, where Z is an electron withdrawing group such as an aldehyde, an ketone and an ester, or a ArSO2, that is the sulfonyl aryl group, and the such as fluorine atom. The mechanism operating in some other cases are different from the established SN1 and SN2. They are described as tetrahedral mechanism and addition elimination mechanism. We shall take this topic in the future modules in very much detail. Let us summarize this module. In this module, we have tried to teach you that SN1 dash is a symbol of substitution for unimolecular attended with rearrangement. SN2 dash is a symbol for substitution by molecular attended with rearrangement. These mechanisms may be appreciable to substitution in allylic system. The stability of the allylic radical can be utilized in the preparation of allylic halides, especially chlorine and bromine. Allylic bonds are often weaker and more easily broken. Allylic halides readily undergo substitution reactions via either SN1 or SN2 pathways. The carbocation formed as intermediates when allylic halides undergo SN1 reactions have their positive charge shared by the two end carbons of the allylic system and may be attacked by nucleophiles at either side. Products may be formed with the same pattern of bonds as the starting allylic halide or with the allylic rearrangement, that is SN1- or SN2- mechanism. Allylic halides react faster than comparable alkyl halides under condition that favor the SN2 mechanism. The reaction is applied to organic synthesis mostly when allylic halide is primary in nature. The label SNI we taught you stands for substitution nucleophilic internal. This is a third mechanism besides SN1 and SN2 which we already taught you. Now SNI students, we told you SNI reaction leads to retention of configuration. A typical reaction is a reaction between optically active alpha phenyl ethanol with thionyl chloride. The product alpha phenyl ethyl chloride has the same configuration as the starting alcohol. Lastly, we taught you that vinylic substrates such as CH2 double bond CHX are essentially inert towards nucleophilic substitution. Now students, we have taught you in detail about vinylic substitution, allylic substitution, substitution at trigonal carbon and SN1-, SN2- and SNI mechanisms.